All right, so in this video, I'm going to introduce section 2.1, which is linear functions and why we in particular care about them. So in calculus, we're going to be very focused on understanding how things change. That's the hallmark signature of why calculus is different from other math subjects. It tries to understand change. So our first concept of change is going to be the average rate of change of a function, and we're going to tie that into linear functions today, okay? All right, so if I have a function f, I can measure the average rate of change of a function f from one input x1 to another input x2. And the way I do that is I determine the output at x2, subtract the output at x1, and divide by the difference of the inputs, x2 minus x1, okay? So as long as the x2s are above one another and the x1s are above one another, that's perfect, okay? Now, oftentimes, especially in physics, they'll call this delta y over delta x. Y is our output and delta means change in. So this is the change in the output divided by the change in the input, okay? All right, so for example, what's happening here is I've got some miscellaneous graph of a function f. Hopefully the green shows up all right. And I've just plotted 2 points, x1, f of x1, and x2, f of x2, okay? And I can measure the average rate of change between those. So why might that be important? Well, let's say I have a function whose input is the year it is, x equals 2025, and the output is the value in dollars of somebody's, I don't know, retirement portfolio, okay? So if I calculate the average rate of change of this function from 2020 to 2025, that would mean I would like the output f of 2025, so that's the value of the portfolio in 2025, minus the value of the portfolio in 2020. So that's the change in the money that the portfolio is worth. And then I'm going to divide it by the change in the inputs, and that would come out to be 5 years. So what this fraction would be telling me is the change in dollars divided by the change in years. Or in other words, it's going to be telling me the average annual rate of change in my portfolio. Maybe it's gain or maybe it's loss, and it's going to be in terms of dollars per year. So if my average rate of change was $50,000 per year, I should be happy because every year I've gained $50,000 on average, okay? But maybe my rate of change is negative $20,000 per year. So on average, every year from 2020 to 2025, my portfolio has lost 20,000, okay? By the way, I should have said pause, copy. Okay, I'll let you pause now. All right, so far, nothing to do with linear functions. But how about this? So pause, copy. All right, so a linear function is one of the simplest kinds of functions we have. It's a degree 1 polynomial, so it means the highest power on x is x to the first. In other words, it's a function of the form f of x equals m times x plus b, where m and b are actual numbers, and we'll find out that they have good meaning as well. If you've seen lines before, linear functions before, you know that this is called the slope-intercept form. So linear functions can be very handy. So first example, we have a basketball factory, and we have daily fixed costs of $100,000. So just to open the factory costs us $100,000 a day. Then each basketball produced cost $4, okay, to produce it. Production cost of $4. So I can set up a function where x is the number of basketballs produced in one day, and c of x is the total factory costs in one day to produce x basketballs. So to produce x basketballs. Okay, so for each x, there's a $4 production charge. So to produce x basketballs, I simply take the number of basketballs produced and multiply it by 4. That's my production cost for the basketballs. But then I have to add to it my production costs of $100,000. Okay? And I'm going to fill in a few values on this table, all right? So if x is 0, so if I open the factory but don't produce any basketballs, my production cost, or sorry, my total cost is $100,000. If X is 1, I think I have 4 plus $100,000. So I have 100,000 and $4. I produce 2 basketballs. I've got $8 for ball costs and 100,000 for fixed costs. So that would be 100,008. And 3 would give me $12 to produce the balls and 100,000 in fixed costs, so 100,012. Okay. All right, and now let me just calculate a couple of the average rates of change. So from X equals 0 to X equals 3, it says take my output at 3, 100,012, subtract my output at 0, that was 100,000, and then divide by the X minus the X, so the 3 minus the 0. The 3 corresponded to the number above it, the 0 corresponded to the number above it. So I think I get $12 on top and 3 balls down below. So I think I get $4 per ball, which makes sense. The average rate of change going from $0, 0 balls to 3 balls is on average a $4 per ball rate of change. And let's just go from 1 to 2 as well. I'll go a bit more quickly here. The output at 2 is 100,008. The output at 1 was 100,004. And over 2 minus 1. And the difference on top is 4. Difference downstairs is 1. So that again gives me $4 per ball. And you're probably highly unimpressed by that. Fair enough. Okay. All right. Next panel. Okay, so the last example illustrated a very special feature of a linear function. So linear functions, sorry, pause, copy. The special and remarkable thing about a linear function is that their average rate of change between any 2 inputs is always the same, okay? So if you've got a linear function, grab any 2 x values, calculate the average rate of change, you'll always get the same number. We call that number, that constant average rate of change, the slope, okay? All right, so here is that slope-intercept form of a linear function. And this value m, that is that slope, that constant average rate of change. We often call it the change in y over the change in x, delta y, delta x, or perhaps the rise over the run, okay? All right, the b also has great meaning. It's the y-intercept. If I plug in, to be on the y-axis, my x value is 0. So if I plug in x equals 0, I get b. So b is the y-intercept. It's where the graph of the function hits the y-axis. All right, so example 2 here. I've got a horribly drawn, trust me, I think it's a line. And I've plotted 3 points, 2, 1, 4, 5, and 5, 7. And I'd like to just determine the slope. So I can pick any 2 points on the line and calculate the average rate of change. Because no matter which 2 points I pick, I should always get the same constant answer, the slope. So let's say I pick the 4, 5, and 5, 7. So 4, 5, and 5, 7. So I'm going to take the second y value, 7, minus the first y value, 5. And I'm going to divide it by the second x value, 5, minus 4, the first x value. So that's the change in my y values over the change in my x values. And if I do the math here, I get 2 over 1, which is just 2. Okay, now you might think to yourself, oh crap, I've got to make sure I do this guy first and then that guy second. It actually doesn't matter, okay? So for example, if I had done the y values in the opposite order, 5 minus 7 on top, as long as I match it up with the corresponding x values underneath it, 4 minus 5, I'll get the same answer. So I get a -2 on top and -1 downstairs, which is a 2, okay? And also, I said it didn't matter which 2 points I picked. So if I pick the first guy and the last guy, let me just quickly calculate the slope there. 5, 7 and 2, 1. So change in y over change in x is what I'm after. Change in the y values was 7 minus 1. Change in the x values was 5 minus 2. So I get 6 on top, 3 downstairs, and that again gives me 2. So my slope, I mean, it's pretty definitively 2, no matter how I decide to try and calculate it, okay? All right, last example. So now we're going to do sort of a full-fledged example. Determine the equation of the line that passes through the points -1, 4, and 5, -8, okay? So pause, get that down, and then I'll work through it. All right, so first, the slope. We just calculated how to do a slope. We just learned how to do a slope. I only have 2 points to select, so there's no real questions here. To calculate my slope, I'm doing the change in my y values over the change in my x values. So I'm going to do my -8 minus my 4. I'm going to do my 5 minus my -1. Change in y, change in x. Let's see, on top I get a -12. Downstairs I get 5 minus -1 is 5 plus 1, so I get a 6. So I get a -2. Okay, so my slope is -2. All right, great. Now, remember, my goal here is to get a linear function. So I need to get an m times an x plus a b. I now have my m, right? So I now know my linear function looks like m, which is -2 x plus b. And I just need to find b, okay? So I can plug in either of the 2 points into my function and solve for b. So plug either point into function and solve for b. So let me just grab, I don't know, 5, -8. You can grab the other one, and if you grab the other point and do it, you'll see you get the same answer. So I'm going to grab 5, -8. I'm going to plug 5 into my function, okay? So I know f of 5, if I plug in x equals 5, is -2 times 5 plus b, okay? So I plugged in x equals 5. I know the output. I know f of -5. That's equal to -8. So I'm going to plug in -8 for f of 5 equals -2 times 5 plus b. I'm going to now try and solve for b. So I've got -8 equals -10 plus b. I could add a 10 to both sides. And I get that b is equal to +2. Okay, -8 plus 10 is +2. All right, so I've got the value of m. I've got the value of b. And so I can combine them into my slope-intercept form. -2 for my m and +2 for my b. And that would be the equation of my line. So we first determine the slope using the 2 points provided. I write out my linear function with that known slope. I grab either of the 2 points and plug in the input and the output and solve for b. Once I have b and m, I can express the slope-intercept form of the function.